Okay, so today we're going to continue our last lecture on looking at the flow field near the aircraft and what is the effect of the bound vortex that goes through the wing. And on Wednesday, we're going to discuss now what is the consequence of that. How does the bound vortex as well as the induced flow near the aircraft affects different design of the planform, including taper, which means the wing gets, the chord length gets larger or smaller as you move from the wing root to the wingtip. Sweep, which means basically the sweep angle is the airplane, the x coordinate or the coordinate in the flight direction, right, gets further and further behind as you move towards the wingtip. That would be like a back sweep, and a forward sweep would be the other way. The wingtips are ahead of the wing root. And also twist, which means the different cross sections are at different angles. So we'll look at that on Wednesday. So today is going to lay the foundation for that discussion, right? So basically the flow near the aircraft really dominates like our discussion on how the planform affects airplane performance. And there is no class on Friday. It's a student holiday, if I'm correct, right? And just a reminder again, the first quiz is exactly 1 month from now. All right. Okay, so the first quiz is going to cover like everything we learned from the beginning of the class up to that quiz. Okay, so let's remind us of what we'll be looking at today and on Wednesday. So if you look closely to the flow visualization on an airplane, you're going to see that the flow near the airplane is significantly different from the flow in the wake. So here you can see the air moves upwards before it turns around and moves downwards, right? So this is the kind of thing we'll be studying why today. Okay, again, this is the domain of the lifting line model, except for instead of just looking at the trailing vortex, we'll be also looking at the effect of the bound vortex. And we'll also look at what is the effect of the trailing vortex when we are getting closer to the airplane. The difference is that when you're firing the wake, the trailing vortex can be thought of as an infinitely long vortex, lying in just one direction. When you are getting close to the airplane, the finiteness of these vortices starts to matter. The first thing we're going to look at today is how does a finite vortex actually, how does a curving vortex? We're gonna see a little bit later that maybe I should state it right now. There is no such a thing as a finite vortex that starts at a point and ends at another point. Okay, so all vortices are either infinitely long, which means they extend all the way to infinity, or they form closed loops. So yeah, we'll look at that later. But no matter it's a vortex that forms a closed loop or goes to infinity. So here, let's consider only the case that the vortex goes to infinity. Then the velocity around the vortex at any point P, right? So this is at the point P, can be computed with a much more complicated formula than what we have been looking at before, right? So what we have, let's compare this to what we have been looking at before. So what we have been looking at before is a vortex of circulation gamma, right? The same gamma as the gamma appearing over here. The velocity at any point is actually equal to gamma not divided by 4 pi, but divided by 2 pi, right? Okay. 1 over the distance. Okay, so imagine that there is a vortex in this, rotating in this direction, right? So using the right-hand rule, the vortex would be going into the board, right? So this is going to be the direction of the vortex. So let's actually use L as the direction of the vortex. So this is L direction of the vortex. All right, and we know the magnitude of the velocity is 1 over the distance. And here, let's use r as the vector that points from the vortex, somewhere in the vortex, to this spatial location, let's say P, right? Same as here. So in the case of an infinitely long vortex, okay, and let's imagine this R points from the closest point on the vortex to that spatial location. So can somebody tell me what is the magnitude of velocity at P for this infinitely long vortex? How does the velocity field around this infinitely long vortex go, right? You know, anybody? Yes? Yes, is that times 1 over the magnitude of r, exactly, right? The strength of velocity decays like 1 over distance. And the circulation gamma means if you integrate over a circle of radius, right, r, which means over a length of 2 pi r, what is that total integrated velocity? That's why the velocity is 1 over the magnitude of r. But this is the velocity as a scalar. What if we want to represent this velocity as a vector? What is the direction of that velocity? Just how can I represent the direction of the velocity, which is, let me use this orange. The direction of velocity is this way, right? How can I represent the direction using r and L, which is the direction of this vortex?
R times cross product.
Cross product, yes. So which cross with which? Like think about L being into the board, right? And R is in this direction. So L cross with R is exactly in this direction, right? So the direction should be L cross R. But now we introduce so let's think of L as the unit vector, okay? L as a unit vector. So L direction, let's say unit vector. Yes?
Why did velocity point like perpendicularly downwards instead of perpendicularly upwards?
Yes, this is because I defined this vortex as rotating this way. Yeah, that's why the velocity here is like that. And that is why the vorticity is pointing that way. If instead the vorticity rotates in a different direction, in the counterclockwise direction, then the velocity would be upwards, but then this L would be pointing out of the board instead of into the board. So you are still going to get L cross with R being the velocity direction. Okay, and now, but the magnitude of the numerator is now proportional to R, right? Which means if I want to make the whole vector proportional to 1 over R magnitude, I have to square the denominator. All right? Got it?
L is looking towards the...
L is the direction of the vortex. In this particular case, if the vortex is rotating this way, you use the right-hand side rule. Your thumb is the direction of this L.
In that case, L times L cross product R is like... No?
Yeah, in this case, if L points inward, R points towards P, then L, R, then V would be downward.
Okay, yeah, I was thinking that.
Okay, right hand rule. Okay, so this is actually the vector form now in 3D. Okay, so now we have to transfer our knowledge from 2D to 3D, right? This is going to be in 3D. What is the formula for the velocity induced by an infinitely long vortex? Okay, any questions on that part? So this is let me just close it with a infinitely long vortex. And today we're going to be discussing vortices in one direction. In one direction. Like L, right? So today we're going to be looking at the vortices that curls around. So, for example, here we are looking at a vortex that, just imagine we have just the two vortices on the two wingtips. We will be looking at a vortex that goes this way, right, from infinity up to the left wingtip, and then it turns around, goes from left wingtip to the right wingtip, and then turns around again, going from the right wingtip to infinity, right? So just to look at my hand, right? So the direction of the vorticity is consistent. Okay, so if you look at my right hand side, my thumb is always pointing towards the direction I'm traveling towards, and these kind of curving arrows represent like my other fingers, right? So I always have this going in the right direction. So this is the effect. This is like what I mean by a vortex never ends, right? So basically it's a single vortex of consistent strength gamma, except for the direction is no longer a constant. Okay, so today we are going to look at this formula. It's called the Biot-Savart law. Okay, so this is let me just this law actually happens not just in aerodynamics, but also in other physical domains. If you look at the electromagnetics, you're going to see something very similar about the like the magnetic field, for example, induced by a current. This is basically the same equation. Okay, but today we're just going to discuss fluid mechanics, and we're going to derive from this equation. We're going to show like this equation is actually generalizes is a generalization of the infinitely long single direction case, which means that if the dl is actually a constant, right, we are able to derive this formula. And then we're also going to derive from this formula cases where the vortex is not in a single direction. Okay, and that is going to explain how the flow field is going to be around an airplane. So let's start by considering just one segment of a vortex. Okay, so let's imagine that segment. Let's actually just think about that segment as one of the three segments. So we are thinking about an airplane with a wing here, with a fuselage, with a so this is my airplane, right? And we have a strength of gamma, and let's just put the coordinates straight. So the x-axis always points downstream, the z-axis always points up, and in order for this to be consistent, the y-axis has to point that way. Okay, so let's look at this bound vortex first. Look at this bound vortex first. The bound vortex would be lying along the y direction. All right. Okay. So let's actually consider two coordinates. One coordinate is in the x-z plane, and let's actually just put that vortex at the center, and the vortex goes into the board. Okay. So can somebody tell me, like, my DL would be, for that particular segment, would point towards inside of the board, right? So can somebody tell me, using the right-hand side rule, and look at this formula, right? What is the velocity induced by a small segment DL that points into the direction? What is the direction of this velocity field in the xz plane? If dl points towards that direction, right, R is the vector that points from the center of the vortex to whatever location I measure in the velocity field. So if you take your hand, first go into the direction of dl, then go into the direction of r, you're going to see the velocity is going to be rotating in a clockwise direction. Okay, and so it doesn't matter. And also, this equation, if you look closely at this equation, it doesn't matter where r is. It always points in the perpendicular direction of r. So let's actually just for numerical calculation, let's actually just take z equal to 0. So let's say p is equal to x and y is equal to let's just say y, and actually let's just take z is equal to 0, right? So let's take a point that lies on the same plane as the vortex. If we choose another point, we just know the velocity magnitude is determined by just the distance, right? So just by the distance, which means x squared plus z squared square root, and the direction is going to be perpendicular to x and z. Okay. And let's figure out this integral. And again, let's take a different view. Let's look at it in the y and x plane. Now we are looking at a case where both the vortex and the observation point are at z equal to 0, right? So that means we can only look at the xy plane. And here we are looking at a case where in the y direction, the vortex starts at minus b over 2 and ends at b over 2, right? Okay, and we are looking at a point that's we are looking at a point that's x and y. All right. Now let's look at a small segment dl. So dl we know points towards the positive y direction, okay, and r is going to be this vector. So r is going to be x would be x, y would be y minus the current, so let's say L is the current coordinate of that small segment. Y minus L would be the y direction of this r, right? And z we know is 0. Okay? And dl, if I make it a vector, that'll be x would be 0, y would be dl as a scalar, z would be 0. Okay? Any questions on these coordinate form of the vectors? Good, right? Okay, so now let's plug it in. Plug in this guy. So dl cross r. First of all, what direction is going to be dl cross r? The z coordinate are all 0, right? Somebody said something? Minus z, exactly. So because the z coordinates are 0, so the x and y coordinate of the cross product are both going to be 0. You don't even have to think about it, right? So if x coordinates are all 0, then the yz coordinates of the cross product will be 0. If y coordinates are all 0, then xz are both going to be 0. In this case, the z coordinates of the two vectors are all 0, so x and y are also going to be 0. So 0 and 0, don't even have to think about it. Okay? And then the z coordinate, the cross product would be this times this minus this times this. All right? Agreed? So this times this minus this times this. And in this case, this times this is 0 because this is 0. So we only get this times this. So in the z direction would be minus x times dl. All right, good? Okay. And of course, I need to divide by r magnitude cubed. So what I would be dividing is by, well, the r magnitude is x squared plus y minus l squared cubed. right? I'm just taking the magnitude of r by squaring this plus squaring this square root. Okay, good. All right. Now we have to integrate, right? We have to multiply by this constant. Gamma is a constant, remember, like over 4 pi is also constant. So v at this x and y location induced just by this part of the vortex would be an integral. So let me just pull gamma over 4 pi out. And the integral is going to be, I'm going to be integrating this dl, right? From minus b to minus b over 2 to b over 2 of let me just look at the z velocity, because we know the x and y velocity are both 0. Okay, and I have minus x dl divided by well, square root of x squared plus y minus l squared cubed. Okay, so now it's time to do a change of variable. Okay, and again, like it's a lot of trigonometry to think about, but like if you have done this type of integral many times before, you're going to notice immediately that we're integrating over the variable L, right? And L appears in a form like this. So it's quite natural to think about changing the variable to a variable that has some kind of an angle, theta. And in this case, my theta is going to be the angle between the x-axis and the r vector. I think this might be my minus theta actually. Let me just yes, this actually should be minus of theta, because I want a yeah, let me do minus theta. So basically positive theta would be for example when L is closer to half b, right? So that way I don't need a lot of negative signs. Right, so when my L goes all the way to here, the theta would become positive. When my L is near negative b, my theta is going to be more negative in this case. Okay, so after the change of variable, we know that the square root of the x squared plus y minus L squared. So that's going to be the magnitude of r, right? The magnitude of r is actually equal to x, right? This is the x coordinate divided by what? Cosine of theta, right? I mean, this is basically saying x, which is this side, is equal to the hypotenuse times cosine theta. So after you perform the change of variable, basically what we get is this would be gamma over 4 pi. And now it's interesting, like the bounds of the integral is really can be thought of as two angles, right? One angle is let me say this is minus theta L, and the other angle is this is theta R. So basically the theta, the angle, right, from the left wingtip and the right wingtip. Okay, so this would be theta L to theta R, and I have a minus x, and okay, so what is dl? Dl, I have to right. So let me first say a little bit like what is L. So L minus y. Actually, let me just do the other way. Yeah, actually, L minus y. L minus y is the vertical, is the y directional displacement between P and the segment of vortex we are integrating. So that is actually equal to x, the other x coordinate, times the tangent of theta, right? Agreed? So dl would be dx times tangent theta, and the cube of this thing would be cube of x divided by cube of cosine theta. Alright? Okay, so further simplification, gamma over 4 pi, theta L, theta R, and x, they cancel out each other, except for there is going to be one x in the denominator, and the derivative of tangent theta is d theta over cosine squared. Okay, so it cancels with 2 of this cubed, and only one cosine theta remains, d theta. Alright? Correct? Alright, okay, so let's further write it down. Now what is the integration of cosine theta? Let's actually write it down. Gamma over 4 pi, and x can also be pulled out, right? And there is the integration of cosine theta, it's sine theta, right? And there is a negative sign, which means we can just reverse the left and right. So it'll be sine theta L minus sine theta R. Okay, so that's basically the formula actually for generally what is the induced velocity of a vortex of finite length. In fact, you can think about this finite length, right? It actually doesn't, if you take the limit of this finite length, you can actually get the same formula for an infinite length vortex. Why? This is because if the left wingtip extends all the way to infinity, and the left wingtip extends all the way to plus infinity, what is going to be minus theta L? What is theta L at the limit of this wingtip going all the way to infinity? A 100 and either way, right? So theta is the angle between the x-axis and this guy, right? 90, right? So minus theta L is going to approach 90 degrees, which means theta L here is going to approach minus 90 degrees. And the sine of theta L is going to be approaching what? -1, exactly. Okay, so at the limit of the left wingtip going to infinity, sine theta L is going to approach -1. How about the right wingtip? If the right wingtip goes to the other infinity, what is theta L? Theta R. 90 degrees. What is sine of theta R approaching? +1, right? Then in this formula, I would get -1 minus +1, right? -2. That -2 cancels with 4 here to get 2 pi x. That's this, right? Okay, is this because the magnitude is gamma over 2 pi, right? It's gamma over this 4 becomes 2 after cancellation with this. And x is what? X is the distance from the observation point to that infinitely long vortex, right? So in 2D, that's going to be exactly this formula over here. Okay, good. Let's consider some other scenarios. What if I have a vortex that is only infinity to one side, but on the other end, it ends exactly at the same y position as my x, my observation point? In that case, still, what is theta L? Still going to be -90 degrees, right? So the sine theta L is still going to be minus 1. But how about theta R? 0, right? Theta R is going to be exactly 0 because I'm ending exactly at the same horizontal location. So R is going to be in the x direction. There is 0 angle between the R direction and the x direction. So I would be getting minus 1, minus 0. So the velocity induced by a semi-infinitely long vortex, right, that ends at the orthogonal location as my observation point is exactly half as much as an infinitely long vortex, which makes complete sense, right? Because if I add the two parts of this semi-infinite vortex, I would get the full velocity induced by the infinitely long vortex. Okay. Of course, the most complicated case is when both sides are not infinite, right? So, for example, let's consider the case where I'm looking at a point. Okay, so let me just draw some scenarios. So the first scenario we considered is infinitely long. So we're looking at a point where like this is minus theta L is approximately 90 degrees. The other is this theta R is also approximately 90 degrees, right? This vortex is going to be infinitely long vortex. Infinite vortex. What we get is V equal to gamma over 2 pi x, right? So this is case 1. Case 2 is semi-infinitely long vortex, so it ends over here. And I would get minus theta L is also almost equal to 90 degrees. But I have my, well, it's hard to draw, but theta R is equal to 0 degrees. So my V is going to be gamma, oh, there is a minus here, I forget. The V here would be minus gamma over 4 pi x. Okay, and let's just consider one other case where the vortex is, let me just, the vortex and the observation point forms a equilateral triangle. Okay, so this is P. This is the end of the two ends of the vortex. Again, the vortex goes like this. In this case, my minus theta L is equal to 30 degrees, and my theta R is also equal to 30 degrees, right? What is going to be the velocity here? If it's gamma divided by 2 pi x, that will be exactly as strong as this one, right? It couldn't be. Right. 4 pi x. So this is because sine of theta L is going to be minus half, right? 30 degrees. Okay. And sine of theta R is also going to be half. So I get pi minus pi over, again, 4 pi x. So this vortex has exactly the same effect as the semi-infinitely long vortex. All right. Hopefully that kind of gives you some intuition on like how much velocity like a finite length vortex induces. Okay. Let's actually spend the remaining part of the lecture doing some exercise. So imagine again, like I have this airplane here, and the flow near the airplane is described by this 3-segment vortex, right? We call it a horseshoe vortex. Basically, let me see, what is the direction? The direction actually, gamma would, the right side is actually, the gamma should be pointing this way from the right side, right? So if you think about the flow goes down in between these two vortices, right? The gamma should actually go that way, right? Okay. Let's consider several points, and for all these points, let's think about what is the effect of all the vortices. And let me just copy what we wrote down before. Let's move it left a little bit. Yeah, and see if we can figure out what are the induced velocity at the 5 points. The first point is far downstream, so that's like very, very far downstream, right? And right in between these two vortices. The second point is still right in between these vortices, but not as far downstream. It is equidistant to all the three vortices. Okay? And the third point is near upstream. So it's actually upstream of the center of the bound vortex for half of the span. And the 4 is in the z direction above the airplane, and 5 is below the airplane. So please form groups of 2 and work out as many of the induced velocities as you can. Actually, all of them using exactly this formula. Okay? Please come over. Chalks here. More chalks here. Chalks over here. Yeah, that's right. I mean, the most important thing is to figure out what these angles are, right, for each of the 3 legs of the vortex.
Can I ask a question?
Yeah.
This thing like extends to infinity.
Yes,
right?
yes.
Okay.
Yes. Yeah, the 2 vortices starting from the wingtips, they go all the way to infinity.
Okay, so are you
Maybe let me draw what the angles are again. Yeah, just reminding you like what the angles are again, right? So if we draw the vector from the vortex to the point, from the vortex from the nearest point to the vortex, right? These are the directions that form the angles with that these 2 vectors that points from the tip of the vortices to that point.
we have 19 here? Yeah, and like 19 here. Yeah.
So which vortex are you considering first?
The first one. And the other one would be this, right? Yeah. Okay. We just
Yeah.
But this is infinitely away.
Yeah, yeah.
So it's 0 and then distance. 2.